how to integrate first order equation with cluster coefficient. If I give you this equation, dt, no space equal omega f minus equilibrium, and f equilibrium can be thought as a constant on the time scale delta t. I hope I don't need to show you that this is the solution, do I? But you can believe it. That's right. So basically what this does, like, if I start with addition, condition at time t, I have an exponential decay, which is dictated by omega. And in the long run, if omega is positive, this will go, and I'm left with a steady state, which is equilibrium. So this is the long-term steady state of the system, except that f equilibrium itself is changing, so this system is evolving in time, but there is the mechanism for get the initial condition and be absorbed, so to say, by the steady state in a time scale 1 over omega. In Lattice Boltzmann, that would be an exact integration within the scale delta t. Very often you do what is called Euler time marching, which is a first order integrator. And you replace the exponential with the first order expansion. And here you recognize the structure of the Lattice Boltzmann, because I think I did write at some point this expression. And this means x plus c delta t, t plus delta t, okay, shifted. Of course, this is the integration along the trajectory. It's not a simple time derivative. So t plus delta t means that I'm moving space and time. Okay? So it's the integration along the trajectory. But the structure of the time integration is the same. It means that if at time t I'm here, with a certain value f of t, by the time I move along the trajectory dictated by v, time plus t delta t, there will be a contribution by the initial condition weighted by this exponential and a contribution by the local equilibrium, essentially like this. So if the local equilibrium is here and f is here, I will be doing basically that. Okay. This is time along the trajectory, and this is tau equal 1 over omega. Now, by the time I replace this with the first order expansion, I immediately realize that I have a limitation in the delta t. I cannot take long jumps because I replace the exponential with the first order polynomial. And I'm sure, almost sure, that you know that in order for this scheme to be stable, I have to make sure that this coefficient is smaller than 1, otherwise it's easy to show that instead of having an exponential relaxation like this, if I take small steps, it will be okay. If I take large step, I will do something like that. These things can blow up. The condition for stability is that T is less than 1. Is this known to you? Or, yeah, I think it's very plain. So, no?
Yes, I just
Oh,
wanted to
yeah,
say, if we say we keep the delta t as 1, then omega should be always between 0 and 2, less.
Yeah, that's what this would be. In fact, with the Lattice Boltzmann, delta t is 1 by definition, so omega is between 0 and 2. Okay? So that's plain Euler integration. Okay. Now, there is a very direct connection between this and the stability of the scheme. Now, I have too many equations. Yes, but just forget about everything except this. There are many ways of writing Lattice Boltzmann. The one I like best is very compact, is f hat equal f prime. That is Lattice Boltzmann, that is Navier-Stokes, and that is Turbo. So what is f hat? You know, f hat is f shifted. And f prime, what did I do here? I just take f, bring it to the other side, and I could call, let me put it this way. This is the change in f due to collision. So I can call this f prime after the collision minus f, because it's the change. So this is f prime minus f. So minus f and minus f go, and what I'm left with is f hat, the shifted f, equal f prime, which is f after the collision. So I do the collision, I'm F prime, and I go. Stream will collide the stream. Of course, that's a very symbolic and proper notation, but it really tells you how even the code is done like that, right? You collide and you move. Now let's take a closer look at F prime. F prime is a linear combination, as I said before, of F, so the initial condition, and the final condition. Now, you immediately see that there is a very plain constraint of realizability because each of these guys are just wearing different hats, but they are all distribution functions. They are all supposed to be positive. You don't want any of them to become negative at any time, right? Just by realizability, because they are probabilities. So suppose now I start at a given time in my simulation where F is positive, and F equilibrium is also positive. Would you please tell me if there is any danger of turning two positive quantities into a negative one? For the moment, I just ask you for a yes or no. Is there any danger? Oh, you must know.
Well, for omega larger 1, you turn it
Obviously.
into a negative form.
My omega larger than 1 is just, I think it's called convex. So if this is F and this is F equilibrium, they are both positive. Omega 0 will keep me here. So F prime, I think I've given a picture. So if omega is 0, F prime is just F. So it means I've done nothing. Collisions, no collisions. If omega is 1, I'm just at equilibrium. So omega 0, I'm just here. Omega 1, F prime is just a local field. And if both are positive, there is no way I can generate a negative positive. So this is the safe region. But we know that Lattice Boltzmann can go up to 2. And I will show in a moment that you have to go very much into this regime. So this is the under-relaxation regime in numerical analysis terminology, where you are always safe. I mean, we do not break positivity. If by some reason, and you have to do that, you have to work in the unsafe region, omega between 1 and 2, then in principle you can break this constraint. So the question is, do I have to do this over relaxation in order to do my simulation? And the answer is pretty much yes. So this is just the same story in even clearer format. So essentially, once again, if omega is 0, I just, post-collision is just nothing, I mean, it's just the same thing. Omega 1, I just go straight to equilibrium. Omega equal 2, the barrier, means that I'm just jumping the other way. So this distance here is F non-equilibrium. So blue is F, red is equilibrium, and green is F equilibrium minus F non-equilibrium, so which is in fact, we can read it off from the analysis. So with omega over 2, I just jump on the other side, exactly on the other side. So this distance, which is F non-equilibrium, is equal to this distance. If you do that, what is the viscosity, nominal viscosity when I do that? You're not supposed to know, but I just want to remind you, I have it somewhere. Exactly. Wow. Very good. I'm happy with you. Seem to be catching up very well. The viscosity is this, right? So this is a constant, you don't mind. And we could write it like that. So when omega is equal to, I'm meeting singularity. If I do that, in principle, I should generate a fluid which is relaxing instantly. You see how crucial the factor minus 1.5 is. It would be a totally different story than that. Okay. In the early days, we thought with vector you could do that. Oh, smash. You cannot do that. If you do that, you are unstable for sure, immediately. The question is, how far can I keep from this barrier? And I can tell you that here there is an H theorem, here there is none. in principle. In fact, Calvin found out that there is one, but in principle you would not expect that. And let me anticipate that if you want to run high Reynolds number, you have to be pretty close. You want to know how close? 10 to minus 3, 10 to minus 4. So you have to be 2 minus 10 to minus 4. If you want Reynolds order 10 to 4. So Lattice Boltzmann for high Reynolds 4 is constantly walking on the edge. That's why I say we were really very lucky, because from year to year there is a priori no guarantee that the method should respond reasonably. And we didn't have a clue of that, I promise. Okay? Now, why is that? I will be more specific. But formally you can see that f prime goes negative as soon as non-equilibrium exceeds this fraction of f equilibrium. And in terms of tau, omega 2 means tau 1.5, so it means that f non-equilibrium can never exceed f equilibrium. But if you, on this side, f non-equilibrium will be greater than non-equilibrium, but then you would exceed just the stability bound for the R. Okay. So, now why do we have to walk closer to the edge? This is a simple exercise which I will do for a long, long time, so you please check on me and we do it together. The exercise is, what is the value on the viscosity which I have to put in my code, given the Reynolds number. I choose a Reynolds number and I want to understand which value of viscosity latitude factors. So let's go quietly through that. So in the code delta T is 1, so I can replace this by 1, and in most lattices CS squared is 1/3. So if I take 1/3 here and 1 here, and if I'm not mistaken, I will check on you please, tau lattice Boltzmann, so code units, is 1.5 plus 3 times the viscosity. So 0 viscosity, tau equal 1.5, and then write on the green ball of the previous time. Now, the Reynolds number is a number, so I can express it in any units I want. If I take everything in Lattice Boltzmann units, it is this, and there is one little step here. The Reynolds number is UL min. Now, Lattice Boltzmann units means I have n grid points in my simulation along one dimension, and the length of my system in centimeters is, say, 100 grid points, and my delta x will be, if my delta x is 1 centimeter, I am simulating an object which is 1 meter long. Okay? So n is nothing but the length of Lattice Boltzmann units. Is that clear? So, Lattice Boltzmann velocity, length, and viscosity in Lattice Boltzmann units. Now, how many grid points can I reasonably afford as we speak? Say 1,000. 1,000 cubed is a pretty serious simulation this day. Right? So NLB would be order 1,000, cannot be 10 to 9, right? In 3 dimensions. And suppose I want to add Reynolds number 10 to 4, which is again pretty serious. It's not a joke. 10 to 4 in 3 dimensions. And ULB I have not much freedom on that. At best I can choose order 0.1, 0.2 maybe. But because of the local equilibrium which are polynomials and can go negative, I cannot make this 1 or 10. No way. So if you now plug these numbers, 10 to 4, 10,000, 0, 1, you get, I hope I'm correct, please check on me, because so that's 0.1 times 1,000 makes, yeah, that's correct. So you see the viscosity is ordered 001, which means in physical units, of course, means that the viscosity in physical units is 001 delta x squared over delta t in centimeters squared per second. Okay. So this so far this doesn't tell you anything whether this is water, air, square of that. Actually, we don't want to know. All we want to know is range. That's a major source of confusion. I got so many emails. Most of the email I get regarding my book is just on the units. But this is clear for you. So now at this point the stories stand out because if I tell you that unit is 001, it means that tau L B has to be 1.5 the frontier plus 003. Okay? So you are pretty close, and very often, in fact, this is typically 10 to minus 3. This is typically 1 over n in actual practice. This is not really capturing, this is really zero-sum approximation. Typically, the rule of the thumb is that with 10,000 grid points, you should be around 10 to minus 3, and you cannot make it smaller. So you see we are pretty close to the boundary, and just because of the limitation I've mentioned. I mean, I cannot make you, if I would make you larger, I could make me larger, right? I could go away from the, but I cannot. And this n is given by the technological limits. If I had a computer where this is 10 to 9, I could take mu as large as I want, but I cannot. So with the present limitation, and this limitation are pretty stringent, they are not going to change drastically any soon. Okay? So Lattice Boltzmann for turbines will be bound for many years to come to work close, to work definitely in the region where in principle there is no H theorem, and very close to it. Is that clear? Okay.
I have a question about the ULV.
Yes.
Here we choose, I'm just a bit confused that if we use this U, if we are going to solve a problem with the Navier-Stokes solver, we use U different or the same U?
No.
I
we use U
want to know
different.
if it is scaled or not here.
That is the source of confusion. And I must say, Lattice Boltzmann is confusing. Because the fact that there are no natural units means that in molecular dynamics, a unit is a Leonard-Jones radius, which is 0.3 nanometers per hour, it's a physical quantity. Here, delta X is up to you. Which means that if you have, let's do the exercise. Suppose you want to simulate, let's say, 4 past the car, and you say the car is 1 million, okay? And you can afford 1,000 million pounds, right? So that would give you just what I said. Your delta X here would be 0.5 centimeter, period. So this is not a physical quantity. This is dictated by your in Navier-Stokes, well, how do you normalize things? I mean, in spectral codes, for instance, your length is 2 pi, typically. So, what does that mean in terms of delta X? N plus, I think it's basically the same. How is it? Yeah, I mean, if I take 1,000 spectral point, I don't remember now. Why is the length? I remember that the length is 2 pi, typically the no-dimensional length in the spectral code, and your Kn is the length over, I don't remember, I don't want to say that. 2 pi is around.
Yes.
Yeah.
Right? But then I get confused. I think the spectrum, I would just mix up.
You scale with that.
Yeah.
That's
In the spectral code, you keep the L fixed. When you take more grid points, you basically go to higher Fourier modes.
Yeah, yeah. Well, but that because you're doing a continuum limit, but you could also be doing a larger schema. So for Navier-Stokes, it's a long time. I don't run Navier-Stokes code, but the theorem is without dimension, with the physical velocity scaled by what in the Navier-Stokes code. think you
Probably.
just choose a reference speed. Say my car is moving at, say, 100 kilometers per hour, and you scale it like this.
For a spectral code, you typically get U0 from the energy maximum.
Yeah, but, yes. But I mean, in a typical lattice, in Aristo's code, there typically there's a delta x, delta t in the code is not one, delta t typically is a small number, these are numbers. So the way you make your code units non-dimensional is different. But typically you choose a typical velocity, a typical time scale, and you normalize with that. In Lattice Boltzmann you say delta x is 1, delta x in the code is 1, which means that, that's what I said. The actual value of your delta x will depend on the size of the problem. I think the same is true in Aristotle. And time is the same thing, because time is typically done through the velocity. So the physical velocity will be the ELV velocity, delta x of delta t. And the typical, for instance, suppose you do it with the sound speed, okay? So let's say that the sound speed CS is sound speed at B, delta x delta t. So the sound speed could be 300 meters per second. This is 1 over square root of 3, delta x you fix, and by that you get delta t. That's the way you do it. But in the code is always 1, so that is confusing.
And at the end, the velocity is, for example, for the physical viscosity, is equal to this. But is it true for also the velocity?
No. In fact, sometimes we can do the exercise. I'm not sure that very often, in fact, the physical viscosity that you get outputted is not matching, say, the air viscosity. What is there? 10 to minus 5 centimeters squared per second. No. Very often you get a different number, and that's a source of confusion. But as long as you are dealing with incompressible flows, where the only thing which matters is Reynolds, you should not bother about recovering the air viscosity rather than orgone viscosity. That's not the point. And very often, what really matters is the combination of the three. As long as this number is the same in your computer and in the experiment, then you're fine for incompressible flows. If there are more quantities to take care of, then you may run into trouble, because there are more dimensionless numbers that you have to make equal between the simulation and the experiment, and this can be a problem. But in this case, I really don't need to know what the physical viscosity is. I really don't. But let's do it. Let's do it. I don't know what I'm getting, but again, please check with me, because long time I don't do these things. Let's do that for this exercise. So it's just like an assignment. So let's say that we have the car, and let's say that air is 300 meters per second with sound speed. So I will choose my delta x according to this. So L is 1 meter, and say that I do a 100 cube simulation. So, 1000 cube simulation. So this tells me that delta x is 0.1 centimeter. Okay? Fixed. Now, how about time? Time, I say that the sound speed is the sound speed lattice Boltzmann, delta x delta t. So this is 300 meters per second. This is square root of 3, which I take 1 because I'm lazy. And that gives me, let's keep the square root of 3, nonetheless. So delta x is delta x, and delta t is here. So I get delta t equals 1 over square root of 3. Delta x is 10 to minus 3 meters. And this is 3 times 10 to the power 2 meters per second, which gives me 10 to minus 5 over seconds. Is that right? Please check on it, I'm not sure. Yeah, looks like it's 2 microseconds. So what is the viscosity of this point? I have no clue. We'll figure out. The viscosity is the viscosity of B, delta H squared over delta T, which is, let's do it plainly, so viscosity LB, no, sorry, and I've chosen the viscosity based on this criteria, so I know that my viscosity LB is 001 because I want to have the same understand. So Reynolds has to be, this is a datum of the topic, Reynolds 10/4. So at this point I will have 001, this is 10 to minus 6 meters, and this is also TGS, it's order 10 to minus, no sorry, this is 10 to minus 3 meters, so square is 10 to minus 6, correct? This in seconds is of the order 10 to minus 6, so my viscosity is 001 meters per second, which is not viscosity there. But why it is not viscosity there? It is the velocity of my car. 0.1, 10 to minus 3 over 10 to minus 6, and 100 meters per second. The velocity is not the same. I'm saying 100 kilometers. Well, we have to check that this is consistent with the rate. But if you want, we can spend a few minutes on doing line by line. Is that possible? No. But the point is that I will probably screw both the viscosity and the velocity. I will screw up anything, everything, but I will not screw up the ratio. I promise. This is a major source of trouble for me. I got so many mates about that. But in my book, I put a little appendix on how to do the units, but manifestly, that was not very successful because either people don't read the appendix or the appendix is obscure. I'm just explaining it. But anyway, the point I wanted to make is that no matter what you do, I promise you that the computational resources available, you will always have to work very near the edge where the method was not supposed to work. So here comes Carling, and I understand, I'm already overspilling. Shall we on? Let me see if I can tell you this in a sensible way. This is not so intuitive. Do you have a better picture for that? No. So I have to leave with this. Okay, let me try to do with this picture. Now, collision update. Suppose I have an entropy function, suppose. And these are the contour line of the entropy. Suppose you have just like a nice bottle, and this is just the bottom point of the parabolic. So here the entropy is, minus entropy is minimal, and that's where I want to go. The equilibrium, again, here I should have given some notion of kinetic theory. When the system is at equilibrium, the entropy is maximum. Second case. The equilibrium is the state where at some point the entropy stops increasing because it thinks it's maximum entropy. Then the system then the point where the system has maximum entropy. And I want to make sure that any move in this plane is such that the entropy will not go down. That's the second case. Suppose I start from a point here, F is here, so this is the kinetic space. F1, F2, I would have 18 population. Entropy is a high-dimensional space, but these are the entropy contour in this dimensional space. If I start from here and I do an update with omega equals 0, where do I go? Just based on what I told you before. Please. Post collision is 1 minus omega f plus omega f equilibrium. So if I do a collision with omega equals 0, I just don't move. Right? If I do a collision with omega equals 1, I just walk downhill to equilibrium. And you would say, wonderful. What else? No. If I do that, my viscosity is pretty high. That's the weird thing. Don't forget, viscosity goes with work around 1.5. With omega equal 1, in lattice units I'm basically 1.5, or Reynolds with low Reynolds number. That's very strange. I have to go over, I have to move, I have to overshoot the equilibrium if I want a small viscosity. If I overshoot heavily, crazily, up to 2, I just go on the other side of this curve and I'm walking just exactly this distance. This is omega equal 2. Right? Same distance. Just walking exactly on the other edge. That I cannot do. This is zero viscosity. No simulation will forgive you for attempting zero viscosity. Then the question is, I know that I have to back off a little bit, very little, because if I back off too much, my Reynolds will be miserable, very low. So what Calvin did, that's really very beautiful, is the following. If I do that blindly, I do not know whether by backing off I'm still increasing entropy or not, because before Entropic, there was no notion of this entropy contours. So the procedure is the following. Start from F. He gives an expression for the entropy in the lattice, and based on that expression, you can compute where the so-called F star, there is another quantity F star which has the same entropy as F. So it's a partner. Okay? This typically will correspond to omega, which is less than 2. Okay? But since you know this F star, you are guaranteed that if you don't exceed F star, you will never decrease your entropy. So it's just like setting, I would say, a fence for your move. You know that omega equal 2 is too far, no way. So you compute just the farthest distance you can walk before entropy will start decreasing. Perhaps a one-dimensional landscape, which is of course deceiving but useful for the graphical purpose. If my entropy, suppose my entropy landscape is something like that, okay? This is the equilibrium. And I start from here. Okay? If I do the move at 2, so this distance, I would end up doing that. But if I do the move at less than 2, say, suppose that suppose that 2 is here. Okay? So this is 2 in omega units. Let's see, how do we do that? No, it has to be 2, it's further than that actually. So F stars is here and it corresponds usually to something less than 2. So I have to find the F star such that I'm just on the top of the hill and I know that if I move, so this will be 2 minus epsilon, I know this epsilon and I know that I will have to move at most up to this distance. But unless I have this landscape, I cannot compute F star. So you see the usefulness of this. We did that totally blindly. We moved in a favorable landscape without knowing that the landscape was there. That's why we were forgiven. So here systematically, for each F, you find a fence, and you know that, I mean, I should show you some map, but I have no time. That doesn't really matter. You read the paper eventually. I know that if I make the move to omega 2 minus epsilon, and this epsilon is known, I will have 0 viscosity. So this is F star. Here omega is not 2, it's less than 2. But I know what it is. Then I back off from there. And my Reynolds number will be in fact very high, still very high, but I know that I'm in a protected region. because I know that my entropy, I'm working with a region where the entropy is in fact, here it's a negative entropy. So basically I'm doing this. The way you achieve zero viscosity is very strange, it's very different from the continuum. In the continuum, if you want to go to the bottom, you will do very small steps, and that will be the way the steepest descent. Right? In the discrete time, you have to do very different procedure. I mean, if you do that, your Reynolds number is already low. So you have constantly to overshoot, and the entropic principle, the entropic entropy function, allows you to do that in a controlled way. That's really very good. And when you run it, is there any question? This is really important. I realize I'm a little bit obscure because you should see the mathematics, but that is the principle. So set the fence and move within the fence. And the fence is dynamic, like take every point and every time step, you have to compute that. So it costs you some work. But you are safe and guaranteed that you will never violate the second principle. Okay?
What are alpha and C?
Oh no, don't try to do, don't ask me to do the math because that will be long.
No, what are those quantities? Alpha and C.
C is the collision operator because this would work for any operator. And alpha tells you, because the collision operator, but then we become, I would really need more time. The collision operator, it tells you, in fact, along which direction in this kinetic space you're moving, and alpha tells you the amplitude. It's just a relaxation procedure, but it's a relaxation which is every time self-guided by the criteria that you really don't want to go over the board in the entropic landscape, and this entropic landscape has to be known. And that's what Carlin and Prof were interested in. When you run the thing, the beautiful, please spare me the mathematics, that doesn't take long. Formally, this is just like adjusting omega every time and every lattice side based on, it's a sort of turbulence model in a way. It is not a turbulence model. It's a way of correcting your local viscosity in such a way that you are never unstable. And here some people got ferocious, said this is not direct numerical simulation, because in direct numerical simulation the viscosity is given. This is the pure form of it. I couldn't disagree more with that. In the first place, any numerical method has some fix up. When you really push it hard, if you don't push it hard, everything works. But when you push it up, pseudo-spectra, no matter you name it, any method has its tricks. This trick is very elegant and is physically grounded. That's why I like it. It's a fixed, no question. But it's based on the second principle, not just. One way of doing, very rapidly, I do the plate with an aggressive omega, F prime gets negative, I fix to a positive threshold, and I go. Fix up. It works, but
Since it's a relaxation process, is it possible to reformulate it in an implicit fashion, like using the
Yes.
Patanka trick? And
it is the Patanka trick.
you multiply the right-hand side with an F prime over F, and then you resolve it algebraically to have an implicit formulation of that. But then that shouldn't have any stability requirements, right?
I cannot answer this. I do know.
But there are implicit formulations to the up.
There are implicit formulations of this as well. You gain, can gain in the order of accuracy. But so the main point essentially is a dynamically adaptive procedure which corrects the viscosity, but it does it in a way which is grounded on the second principle. And when you see the code operating, that was really beautiful. We did that a few years ago.
But this is a numerical viscosity now in a sense, and it's
This
tuned
is a
to
numerical
every
viscosity.
stability.
This is a numerical, but it's entirely driven by physics. I'm very sorry.
Okay,
I mean, I don't want
totally
to
agree.
overdo it, but it's very elegant. When you see it in action, you're really surprised.
But how do you prescribe the physical viscosity then in this situation when you want this explicit Reynolds
viscosity
number?
you choose based on your Reynolds,
Mhm.
okay? The viscosity you give, and then, you choose a reference somewhere. I should tell you something more. The entropic method most of the time sits idle. It it just sleeps. It only wakes up when needed, that's the beauty. This is a cavity flow, but never mind. Suppose you have a flow which is green like this, and if you have done the simulation, you know that the critical point is this corner. Typically, you would ruin a simulation because there are local instability here, okay, as you could remember. And if by some reason you can't survive the crisis, then the system will move on. If you watch the entropic method in action, that's what we did, when the crisis is setting up, the correction comes into the game, it fixes the problem just locally, and then it goes. So for most of the time, by far most of the time, entropic is just BGK, same thing. It becomes non-BGK just when and where it is needed, and that's why I like it. It's really very elegant. So the typical result would be,
So it's a bit like a slope limiter and a finite volume Golomov
yes,
scheme.
yes, it is in that way. Exactly. So what did I want to show? Yeah. For instance, this I think is cavity flow, and at a given Reynolds, if you run entropic lattice Boltzmann versus LBK at the same resolution, and this would be the spectrum. I'm not sure this is a cavity, but it gives the idea. See, the spectrum, this is the entropic, and this is the BGK spectrum. You see that the spectrum is not decaying very fast at IK. This is a typical precursor of instability. If you let it go, you will have more energy in the IKs, and that will ruin the simulation. And LBE, in fact, entropic, keeps the thing stable. But this is achieved, you should not think of this as being constantly acting on the system. No, it achieves this by just coming into the play when the crisis arrives. For most of the time, this entropic estimate will restitute a trivial value 2. So the fence needs no intelligence, so to say. So this entropic landscape only shrinks when the fluid is getting critical. When you cannot move too much because the fluid is near to instability, the entropy landscape will shrink. And there you have to know how far you can go. For instance, in the early days, to make a joke on my friend Roberto Benzi, which shows omega 1.89, which I call the Benzi constant, because by some finger we couldn't go beyond that. No coincidence, this is 001. And when we tried to push it, we wanted to do 2. We were naive enough, so now we will go as far as we want with Reynolds. And 189 from that resolution was never from. We had no clue where this number was coming from. Now we know. For another flow, it would be 194. I don't know, but the entropic will know. So that's the beauty. And essentially, what you do, again, this is LBGK with 3 times as many grid points, and we will still stabilize, but 3, factor 3, is a lot. It's 3 power 4 for people. So even though the entropic will cost you more, because each time step, the grid point you have to solve, you have to find F star. And the equation here, h of f equals h of f star, and this is a nonlinear equation in an 18-dimensional space that you have to solve for one parameter, which is f. But usually a few Newton iterations do. Usually, I don't know. It depends. If you are really critical, maybe it will take more. Maybe you will not converge. I do not know. But the scheme has an elegance which is unsurpassed. I mean, if I compare this with MRT, I'm very sorry, I like this much better. You ask me what is the best. To me, but I might be wrong, I like this much better because it's grounded into the field. MRT has no H theorem, has no control H theorem. Here, in my opinion, is much more profound. The cost is comparable because typically finding a so-called isoentropic partner is a matter of less than 10 Newton iterations, so the cost is 3 to 5 times higher, but is more than offset by the gain in resolution.
The convergence for alpha is dependent on the gradients you have in the flow. I mean, it may or may not converge depending on.
This landscape will not be the same at different locations. In most locations, you can take this F star just as F equilibrium minus F equilibrium omega equal 2. Most places omega, the fence would be at omega equal 2. There you can be blind, as we were. Yeah? But in some other places, near the corner, this will shrink. Okay? So, it's a sort of deformation. And in the quiet places it will be like that, but in a critical place it could be like this. You know? And you cannot go beyond that. That means that you are heavily increasing the viscosity by doing that. Some other places you can just touch it. But E will do the work for you. That's much more beautiful. I'm sorry. There is no comparison. It is in the Godwin kind of thing. Well, that's maybe because I like to think of myself as a physicist. I like this better. It's really much more. It is really grounded in the second principle.
Does it assume that you are actually very close to the equilibrium so that the landscape is actually symmetric about F equilibrium?
No, I'm not very close to it. What do you mean I'm close to it? Yeah, I'm very far from it.
So you never assume that the entropy function is symmetric about the equilibrium or anything like
The
that?
entropy function that is not symmetric in general, it's convex. That is true. But the entropy function, in fact, well, I didn't give you any background on kinetic theory or so on. But for those of you who know, it's nothing strange. It's very similar to the entropy that you have in the continuous theory. So that is the entropy function. So it is convex, but why should it be symmetric? I think this landscape is just. And what you have to find, as I said, you have to solve the equation h of f you know because that's where you have seen f equal h in star. So you have to find a place which has just the same entropy level. So here you would not find any solution, right? Here you would find this. So solving this problem for the flows I know of, but not many people have been using Entropic. So that is the problem. One of the reasons is that they don't want to solve the equation. The papers, I must say, are very mathematical. They are not very captivating. But it also depends on what you want to do. But if you're planning for a simulation where you really want to push your viscosity as low as possible, to me, this is the method you should use. If you have no particular demand on your Reynolds number, then just stay with BGK. Many people will badmouth, criticize BGK, many people, certain people criticize BGK very heavily, far too much. BGK is not the best Lattice Boltzmann, of course. But what is best? Depends on your problem. If you want to say if time is your most precious resource, which typically is, especially as you grow in age, then you want to pick up the simplest, right? But if you want to do Reynolds number, time is not the issue. You have to do the most. The scale gives the most stability. And I little doubt that this is a problem. I myself not worked very much firsthand. I had a PhD student years ago, and as far as I can tell, she would write the code in the method. It's slightly more complicated than BGK, but she had the code working in a few days. That's the point. You know how to solve the Newton. You just have to build up the expression and do something. You know how to do it. Okay? But it is not very popular. Very few people use it, except for the theory group and a few other around. No, that's very, very few people. So it's not popular. MRT is more popular because it has been pushed very, very hard, really lot of marketing behind that. But I would say 99% of the Lattice Boltzmann users today use BGK, including myself. You should know your problem. You will not pass your thesis if you don't use the approach. No, I'm joking, but it really depends on what you want to do. And that, I think, basically concludes what I wanted to say. This you don't need to say anymore, so it really, I mean, I'm sorry that I really didn't give you the math. The math is not totally trivial, but it's not very complicated either, so that's it. I mean, if I didn't do that on purpose, but the reason why I like the Entropic is because when we did that, we did the crime, and the crime was fixed, basically. Now we know why we were lucky. Okay, so, any questions? I don't see happy faces. How come? Are you tired or anything obscure? I mean, I've been very cursory, but I'm sure you're not. The point is quite clear. That's a way of making sure that you're never unstable. Feedback system.
People who are feeling unstable can stay and talk to Sauro. Thanks again.
Thank you.